Hey, hello physical science, this is Mr. B, and we are finally on our last section here of chapter 1, and it's called Presenting Scientific Data. So the reason why we need to have this chapter, or this section, is because in our last one we talked about how we make all of our measurements. So once we make all of our measurements and we come to our conclusion, again based off of our scientific method that we went over, we actually have to present our data in some way. So in order for news to be useful, it must be reported in a clear, organized manner. Like the news, scientific data become meaningful only when they are organized and communicated. Communication includes visual presentations such as this graph. So the example they give us here is that we basically have to make our scientific data that we come up with easily accessible and easily communicated to other people, or else what we did basically was for nothing. So if we can run the best scientific experiment that you could ever think of, and if we don't organize it in a way that is useful and makes sense and can be communicated to someone else, then we've basically done nothing because no one can be able to actually tell what we did. So how do scientists actually organize this data in order to make it more accessible to other people? So they do this by using data, tables, and graphs. So this is a huge tool for scientists right here, using data, tables, and graphs. So I'd make sure I wrote that down, that scientists can organize their data by using those two things. And the simplest way to to organize data is to present them in something called a table. So this table will relate two variables, which is a manipulated variable, our location, so this is changed here over there, our city, and our responding variable, the average annual precipitation. So this is really simple. It just looks at different cities across the United States. Again, they change that. That's what we manipulate. They change what city they were in. And what responded in the change in city was the amount of precipitation that they have. So this is a pretty simple way to compare, again, different average annual precipitation that we have in different cities. So that's pretty simple. That's a data table. And a line graph is useful, so this could be kind of almost made directly into a line graph. A line graph is useful for showing changes that occur in related variables. So in a line graph, the manipulated variable is generally plotted on the horizontal or the x-axis, so that's the one that will run from left to right, while the responding variable is plotted on the vertical axis or the y-axis of the graph. So we could make, again, a line graph very easily based off of this information right here, and actually turning data tables into the correct type of graph is going to be something that is going to be a useful skill for us to do in this class. And okay, we just went over that one. And sometimes when we talk about our line graph, the data points in a graph will yield a straight line. So straight line, just really quickly, would be that right there. That is a straight line. If we actually, again, we'll get to that in a second, but that is what it means when it's a straight line. Again, there's not a lot of breaks or anything in the line. So the steepness or slope of this line is the ratio of a vertical change to a corresponding horizontal change, or hopefully you've maybe seen this formula down here, rise over run. To figure out our slope, when we have a line that looks like this, we just find a data point, we count. Again, over here we have our run, we go 1, 2, 3, 4, 5, and then we find our second data point up there, and we go up 1, 2, 3, 4, 5. So we take 5 over, again, and we use our measurements here with mass and volume, and so we have that our slope is just 1 gram per cubic centimeters. And again, this can only be done when we have a line that ends up being straight. And again, it's not always going to be so perfect as to be 1, but we actually have to count between our data points. And if we look here, we have a data point right here. We count over 1, 2 to the right. That's our run. We have 1, 2, that is our rise. So then if we put 2 over 2, it's going to give us the exact same thing. So when we have a line graph that ends up being a straight line, we can kind of or get a ratio of how, again, the increase has occurred. So that is how we find our slope. And also when we look at different charts, we have something that's called a direct proportion. So I'd make sure I write this down. And a direct proportion is a relationship in which the ratio of the two variables is constant. So this relationship in our example here is that the relationship between the mass and the volume of water is an example of direct proportion. So again, direct means, again, they are constant. It is always, they're directly in line with one another. So the example here, a 3 cubic centimeter sample of water has a mass of 3 grams. So direct proportion right there, 3, 3. And then if we keep going, 6 cubic centimeter sample has a mass of 6 grams. Again, directly proportional to one another, 6 and 6, and it's the same with 9 and 9. So direct proportion is when the two things that we're measuring, again, they're directly related to one another, they stay constant. When one is 3, the other is 3. When one is 6, the other is 6. When one is 9, the other is 9. So that is how we map a direct proportion. And you know what? We will go ahead and we'll cut it off for there. So let me know if you have any questions, again, ending with a direct proportion.